Medieval carpenters worked green oak fresh from the forest, never bothered seasoning it, and their buildings stood for 800 years. Modern builders insist wood must be kiln-dried to 15% moisture, or the structure will fail. Both methods work, but only medieval builders understood why. When Notre Dame Cathedral's roof burned in 2019, French authorities faced a restoration challenge that became a research project. The original 13th century timber frame, called the Forest because it required 52 acres of oak trees, had lasted 8 centuries despite being built from freshly felled timber that modern building codes would reject as structurally unsound. The wood was green, full of water, containing moisture levels that would make contemporary engineers insist on years of seasoning before use. Yet it worked. More than worked. It thrived. Dendrochronological analysis revealed that Notre Dame's builders selected oak from managed forests where trees grew under specific conditions that produced timber with predictable properties. They felled trees during winter when sap was down. They converted logs through riving, splitting along the grain, rather than sawing across it, creating beams where every fiber ran continuously from end to end. They worked the wood green because it cut easier and allowed joints that actually tightened as the timber dried in place. This wasn't luck or primitive trial and error. It was systematic knowledge about wood behavior, grain structure, species properties, and seasonal timing that medieval carpenters learned through decade-long apprenticeships and passed down through guild systems. They understood things modern forestry science has only recently confirmed: that how a tree grows determines how the wood performs, that conversion method affects strength more than species selection, that moisture content at installation matters differently than moisture content during use. The irony is sharp. We have moisture meters, kiln sheeters, engineering tables, and computer-aided design software. Medieval builders had adzes, chalk lines, and knowledge passed mouth to ear across generations. Yet their buildings survive while ours require replacement after 50 years. The difference isn't their wood or their climate. It's their understanding of wood as a living material that continues behaving according to its nature long after the tree dies. The question isn't whether medieval wood knowledge worked. Surviving structures prove it did. The question is, what exactly did they understand that we've forgotten in our rush to standardize, mechanize, and control? Modern lumber purchasing happens in stores or from catalogs. You specify dimensions, grade, and species. The wood arrives dried, surfaced, and ready for use. You assume it's appropriate for your project because it meets industry standards. Medieval carpenters made no such assumptions. They went to the forest. The selection process began long before felling. Carpenters examined standing trees, reading bark texture, branch distribution, and overall form for information about internal wood quality. A tree's shape revealed its growth conditions, and growth conditions determined wood properties. Standards: trees grown in managed woodland, specifically for timber production, developed straight trunks with minimal branching in their lower sections. The constant competition for light in dense woodland forced vertical growth, producing long, clear lengths of straight-grained wood ideal for beams and posts. These trees had tight, even annual rings indicating slow, steady growth, a sign of dense, strong wood. Field oaks, growing in open parkland or hedgerows, developed differently. With abundant light, they spread wide rather than tall, producing shorter trunks and extensive branching. Their wood showed wider annual rings from faster growth, making it less dense, but often containing useful natural curves. A crooked field oak wasn't inferior. It was ideal for specific applications like curved braces or ship ribs, where the natural bend reduced the need for bending or steam treating straight timber. The outer trunk regions revealed additional information. Sapwood, the living layer just under bark, transported water and nutrients. It contained high sugar levels and minimal tannin, making it vulnerable to insect attack and rot. Medieval carpenters recognized sapwood by its lighter color and discarded it for structural use. The inner heartwood, dead tissue no longer conducting water, contained concentrated tannins that resisted decay and insect damage. Heartwood's darker color identified it as the only acceptable timber for long-lasting construction. But not all heartwood was equal. The pith, the tree's central core, often contained juvenile wood formed during the tree's early growth. This material, though technically heartwood, had different properties than mature heartwood formed later. Experienced carpenters avoided using timber containing the pith for critical structural members, knowing it was more prone to checking and cracking. Grain orientation mattered enormously. Spiral grain, where wood fibers twist around the trunk rather than running straight, created timber prone to warping and weak in bending. Medieval builders could detect spiral grain by examining bark patterns. If bark ridges spiraled up the trunk, internal grain did the same. Such trees might be suitable for firewood or posts set in compression, but not for beams spanning distances where bending forces occurred. The season of felling influenced wood quality. Winter cutting, when deciduous trees were dormant and sap levels low, produced timber with less starch and sugar in its cells. Lower sugar content meant less food for fungi and beetles, improving natural resistance to decay. Medieval building contracts sometimes specified winter-felled timber for precisely this reason. A 1355 letter to the Archbishop of York requested winter cutting so timber could dry off during the summer, evidence that seasonal timing was understood and documented. Medieval forest management created conditions that enhanced timber quality. Coppicing, the practice of cutting trees near ground level and allowing multiple shoots to regenerate, produced straight poles suitable for smaller timbers and tool handles. Pollarding, cutting trees several meters up to protect regrowth from grazing animals, generated similar results at heights beyond livestock reach. Standards grown through coppiced underwood developed in shaded conditions that encouraged vertical growth and tight annual rings. This managed woodland system, already ancient by the medieval period, represented accumulated knowledge about optimizing timber production. Some rootstocks were maintained for over 1,000 years, repeatedly cut and regenerated. The carpenters drawing on this system weren't randomly selecting trees. They were harvesting from a renewable resource deliberately cultivated to produce wood with specific, predictable properties. Once felled, trees needed converting to usable timber. The conversion method profoundly affected the final product's strength, stability, and longevity. Medieval builders employed 3 techniques: riving, hewing, and sawing, each appropriate for different applications and each requiring different skills. Riving, also called cleaving or splitting, divided logs by driving wedges along the grain. The split followed natural grain direction rather than an arbitrary straight line, resulting in pieces where every wood fiber ran continuously from end to end. This fiber continuity gave riven timber exceptional strength. No sawn surface cuts across grain, creating potential failure points. The process began by examining the log's end grain, identifying natural cleavage planes. An initial split divided the log in half, then each half into quarters, quarters into eighths. 4. Wider pieces. Subsequent splits produced the desired thickness. The result was what modern woodworkers call quarter-sawn stock, timber where annual rings run roughly perpendicular to the face. This orientation provides superior dimensional stability and resistance to warping, because wood movement from moisture changes occurs primarily across annual rings, affecting thickness rather than width. Archaeological evidence shows extensive riving in medieval construction. A high proportion of timbers in medieval buildings show the distinctive ridged surface characteristic of split wood. Viking shipbuilders rived oak planks as thin as 1 inch for longship hulls, combining strength with flexibility that allowed the planks to bend into their vessels' famous curves. The technique wasn't primitive. It was sophisticated materials processing that produced optimal properties for specific uses. Hewing transformed rough logs into squared beams using specialized axes. The process began with rough hewing, standing on or beside the log and striking powerful blows with a broadaxe to remove most of the waste wood. Chalk lines marked the desired final dimensions, giving the hewer targets to work toward. The rough-hewn surface showed deep notches, torn grain, and axe marks where chips were removed. Final hewing with a shorter-handled, single-beveled axe cleaned up the surface, removing remaining irregularities and bringing the timber exactly to dimension. The quality of medieval hewing can seem unbelievable. Some 13th and 14th century work appears almost hand-planed, with crisp corners and smooth surfaces showing only minimal tear-out around knots. This level of precision required extraordinary skill developed through years of practice. Hewing offered advantages over riving. It worked with logs unsuitable for splitting, those with irregular grain, excessive knots, or dimensions that didn't divide evenly. It produced timbers with precisely controlled dimensions, rather than the somewhat variable sizes riving yielded. The slightly undulating surface characteristic of hewn timber also provided better key for plaster and mortar in finished buildings. Sawing, the most familiar conversion method today, was actually less common in medieval construction than either riving or hewing. Saws were expensive, difficult to maintain, and relatively rare. The Domesday Book of 1086 recorded only 13 saws in all of England, remarkable when you consider the massive amount of timber construction occurring. These were likely pit saws used for ripping logs into planks, with the log suspended over a pit and 2 sawyers operating the large blade, one below pulling down, one above pulling up. Smaller bow saws appeared in manuscripts more frequently, suggesting they were more common tools for lighter work. But the fundamental challenge with sawing was its inefficiency compared to riving or hewing. Sawing cut across grain fibers, weakening the resulting timber, compared to riven stock. It removed material as sawdust rather than producing chips usable for kindling or charcoal. And it required significant labor time, 2 men sawing constantly versus 1 man hewing who could work at his own pace. The conversion method medieval carpenters chose wasn't arbitrary. Riving produced the strongest timber but required straight-grained logs without excessive knots. Hewing worked with problematic logs and gave precise dimensions but wasted more wood. Sawing provided perfectly flat, parallel surfaces, but at the cost of reduced strength and wasted material. Understanding which method to employ for each timber and having the skill to execute that method represented knowledge that took years to develop. Perhaps the most misunderstood aspect of medieval carpentry is the use of green wood. Timber worked shortly after felling with moisture content approaching 100%. Modern construction demands kiln-dried lumber at 15% moisture, or less. Medieval builders deliberately chose wet wood. Both approaches work, but for entirely different reasons that reveal fundamentally different philosophies about working with wood. Green wood offered undeniable practical advantages. Fresh-felled oak cut like butter compared to seasoned timber. Axes and adzes, the primary shaping tools encountered far less resistant slicing through wet fibers than battling the hardness of dried wood. Tool edges stayed sharper longer. The work proceeded faster with less fatigue. For carpenters shaping massive beams by hand, this efficiency mattered enormously. Splitting green wood was similarly easier. The moisture content plasticized the wood slightly, allowing cleaner splits that followed grain more predictably. A green oak log could be split with a wooden wedge, something impossible with seasoned timber requiring metal wedges and much greater force. But the real sophistication appeared in how medieval builders exploited green wood's behavior during drying. Wood shrinks as it loses moisture, and that shrinkage isn't uniform. It's roughly twice as great tangentially, parallel to annual rings, as radially, perpendicular to rings. This differential movement can be either a problem or a tool, depending on whether you understand and account for it. Consider drawboard mortise and tenon joints, the primary structural connection in timber framing. The tenon, when cut from green wood, was slightly oversized. As it dried in place after assembly, it shrank. But because the joint was designed with the peg holes offset, drawboard, the shrinking tenon was mechanically constrained by the oak peg, forcing it tighter against the mortise shoulder rather than allowing it to develop gaps. The joint literally tightened as it dried, a self-improving connection impossible with pre-dried timber. Green wood also allowed builders to use a clever material science trick. If a dry, round tenon was placed in a relatively green mortise, the mortise would shrink around the tenon as it dried, locking it in place through mechanical interference. This technique appeared in furniture, where table legs met aprons. The dry leg received a green apron tenon that became immovably locked as moisture equalized. The cracks, bends, and twists visible in old buildings today aren't signs of failure. They're evidence of timber seasoning in place, something medieval builders expected and designed for. The wattle and daub infill panels between structural timbers could flex to accommodate movement without cracking. Plaster was applied, expecting it would need patching as timber dried. The entire building was conceived as a slightly flexible system that would settle into its final form over the first few years, rather than a rigid structure requiring perfectly stable materials. This stands in stark contrast to modern building philosophy. We insist on dimensional stability achieved through forced drying, then try to prevent any subsequent moisture, movement. Medieval builders accepted movement as inevitable and designed systems that accommodated it. Their approach required deeper understanding of wood behavior, but eliminated the time and expense of seasoning large timbers. An impractical proposition given that a 12-inch square beam might take a decade to naturally air dry throughout its thickness. Not all medieval timber was used green, though. Building contracts from the 14th and 15th centuries sometimes specified seasoned timber. Vitruvius, the Roman military engineer, described killing trees by cutting into the heartwood and leaving them standing until sap drained and the timber dried. A technique evidence suggests was practiced in medieval Europe as well. But seasoning was selective, applied when the specific application demanded it, not as blanket requirement. The distinction reveals sophistication. Medieval carpenters understood that some applications benefited from dry wood, fine joinery, decorative work, situations where dimensional stability outweighed other concerns, while structural framing could use green timber advantageously. Modern practice applies one rule: dry wood only, regardless of context. Medieval practice applied knowledge of wood behavior to select the appropriate approach for each situation. Medieval carpenters didn't just know species names. They understood each wood's working properties, structural capabilities, decay resistance, and ideal applications with detail that modern lumber grading barely approaches. Oak dominated structural work not merely because it was available, but because its properties suited timber framing perfectly. The wood is exceptionally strong in compression and bending. Its high tannin content provides natural resistance to decay and insect attack. It splits cleanly along the grain, making it ideal for riving. When worked green, oak is tractable. When seasoned, it becomes nearly impervious to wear. Most critically for medieval construction, oak's movement with moisture changes was predictable and manageable. But not all oak was equal. Medieval builders recognized regional variations. English oak differed from French oak, which differed from Baltic oak. Each variation had subtle differences in density, grain tightness, and working properties. Baltic oak, grown in the cold northern climates of what's now Poland, Lithuania, and Latvia, developed particularly tight annual rings and exceptional density. This premium timber was exported throughout Europe, commanding prices that justified shipping it to Spain and Portugal. Dendrochronology now confirms what medieval builders knew through observation. Baltic oak's growth patterns made it ideal for specific demanding applications. Elm served specialized roles oak couldn't fill. Unlike oak, which performs best when either completely dry or completely submerged, elm actually thrives in constantly wet conditions. This counterintuitive property made elm the wood of choice for water pipes. Medieval cities created water distribution systems by boring out elm trunks, fitting them end to end. Archaeological evidence shows these pipes remained functional for decades, sometimes centuries, as long as water flow continued. The wood's interlocked grain prevented splitting even under the internal pressure of flowing water. Elm's water resistance also made it valuable for ship keels and other underwater structural members. Medieval shipwrights often combined oak for upper structures with elm for portions that would remain constantly submerged. This wasn't random. It reflected empirical knowledge that elm's cellular structure and tyloses, growths that block vessels, performed better than oak in permanent wet conditions. Sweet chestnut appeared frequently in medieval construction, despite being somewhat inferior to oak in pure strength. Its advantages were different: faster growth than oak, excellent resistance to decay despite lower tannin content, and easier working even when seasoned. Buildings in regions where chestnut grew naturally often used it for secondary structural members or internal work. Where oak's superior but expensive timber was unnecessary. Hornbeam, exceptionally hard and dense even for a hardwood, found use in applications requiring impact resistance or wear resistance, mill wheels, tool handles, workbench surfaces. Its density made it difficult to work, but for situations where softer woods would quickly fail, hornbeam was worth the extra effort. Fruit woods, apple, pear, cherry, appeared in joinery and decorative work where their attractive grain and good carving properties outweighed their relative softness. Medieval builders didn't dismiss these as inferior. They recognized them as ideal for specific applications where their properties match the requirements. The sophistication extended beyond mere classification. Medieval carpenters understood that wood from the same species grown under different conditions performed differently. A slow-grown oak from dense woodland had tighter rings and greater density than a fast-grown field oak. The woodland tree was superior for beams carrying heavy loads. The field tree was perfectly adequate for lighter applications and offered potential natural curves useful for braces. They recognized that heartwood's position in the tree affected its properties. Heartwood nearest the pith, formed when the tree was young, differed from heartwood, formed in maturity. They understood that grain runout, where grain angle deviates from parallel with the timber's length, could dramatically weaken structural members even if the wood was otherwise perfect. This knowledge wasn't written in books or formalized into grading systems. It existed in the accumulated observations of craftsmen who spent entire careers working with wood, who learned from masters who had spent their careers doing the same, and who could see the results of good and poor material selection in buildings that stood or failed across decades. The knowledge was embodied, tactile, observational, exactly the kind of understanding that's difficult to capture in written specifications or engineering tables. The transition from medieval to modern woodworking represents technological progress by any objective measure. Power tools cut faster and more precisely than hand tools. Kiln drying produces dimensionally stable lumber reliably. Engineering analysis predicts structural performance mathematically. These advances make building faster, cheaper, and more accessible. But we lost something in the transition. The knowledge medieval carpenters possessed about wood as a material, how it grows, how different growth conditions affect properties, how conversion methods influence strength, how moisture behavior can be exploited rather than merely controlled, largely disappeared when we stopped teaching it. The Industrial Revolution brought mechanization that didn't require understanding wood intimately. Circular saws cut regardless of grain direction. Planers surfaced regardless of fiber orientation. You could produce lumber without reading the wood, without selecting for grain, without considering how the tree grew. The machines didn't care, so the knowledge became unnecessary for production, even if it remained relevant for optimal use. Kiln drying eliminated the need to understand moisture behavior in any detail beyond dried to X%. Medieval builders had to grasp the nuances of how different timbers dried at different rates, how joints behaved during the drying process, how to exploit shrinkage rather than just prevent it. Modern construction dried everything to specification, then designed as if the material was dimensionally stable. Simpler, certainly, but also more rigid, less able to adapt the technique to the material. The guild system that transmitted this knowledge collapsed during industrialization. Apprenticeships lasting 7 to 10 years, where accumulated wisdom passed through demonstration and practice, gave way to trade schools, teaching tool operation rather than material understanding. Written specifications replaced embodied knowledge. The subtle judgments that separated master from journeyman, judgments about which tree to select, how to orient a beam to account for grain, whether particular timber was suitable for its intended use, never made it into textbooks because they couldn't be adequately captured in text. Economic pressures accelerated the loss. Medieval building timescales measured years. Modern construction measures months. Taking time to select ideal timber from the forest, to convert it thoughtfully, to work it in ways that enhanced rather than merely utilized its properties. All of this became economically untenable when speed determined profit. Building codes, paradoxically, contributed by standardizing requirements without understanding why traditional methods worked. Green wood. Construction violated moisture content specifications despite working perfectly well for 8 centuries. Riven timber lacked the dimensional precision grading rules demanded, even though it was stronger than sawn alternatives. Traditional techniques were outlawed or marginalized not because they failed, but because they didn't fit the regulatory framework designed around industrial materials. Most fundamentally, our relationship with time changed. Medieval builders expected their work to last centuries. That expectation justified investing in knowledge about optimal material selection and use. Modern construction often targets 50-year lifespans. The superior longevity that deep material knowledge could provide becomes irrelevant if replacement is planned within decades anyway. Medieval carpenters working green oak fresh from the forest weren't being primitive. They understood that wood containing 100% moisture cut easier, split cleaner, and could be used in ways that exploited shrinkage rather than fighting it. Modern insistence on kiln-dried timber isn't wrong. It's just different, optimized for different priorities in a different construction context. Both approaches work, but only one required deep understanding of wood as a living material that continues behaving according to its nature long after the tree dies. Medieval builders needed that understanding because their tools and techniques demanded it. They couldn't force wood to comply through climate control and adhesives. They had to work with its properties, which meant first understanding those properties thoroughly. We gained speed and consistency when we mechanized and standardized. These are genuine benefits that make quality construction accessible to more people than ever before. But we lost the intimate material knowledge that let medieval builders read a forest and know which trees would produce the best timber, split a log, and understand from the sound and feel whether it would cleave cleanly, work a green beam, and predict how it would move as it dried. That loss matters less when we're building structures designed to last 50 years. It matters enormously when we try to restore medieval buildings, or when we want to build new structures that will still stand 8 centuries hence. The knowledge isn't completely lost. Small communities of timber framers and heritage craftsmen maintain it. But it's no longer mainstream, no longer something most carpenters learn as fundamental practice. The medieval understanding of wood wasn't better than modern knowledge. It was different. They understood wood behavior through direct observation and accumulated experience. We understand wood through microscopy, moisture meters, and mechanical testing. Both forms of knowledge are valid, but theirs captured nuances about how specific trees grown under specific conditions would perform in specific applications. Knowledge that our more generalized statistical understanding often misses. The 800-year-old oak beams in Notre Dame survived because medieval builders understood wood deeply enough to work with its nature rather than trying to control it. That's not primitive. That's sophisticated materials science practiced without instruments or engineering tables, relying instead on knowledge passed through generations of craftsmen who lived with wood every day of their working lives. We could relearn it. The trees still grow. The properties haven't changed. What's lost isn't the knowledge itself, but the systems that transmitted it. The apprenticeships, the guilds, the expectation that understanding materials mattered as much as operating tools. Those systems shaped craftsmen who could look at a standing oak and see the beams it would yield, who could feel a split beginning and redirect it by shifting pressure, who could predict a building's settling over its first decade from how the timber behaved during assembly. That depth of material understanding represents something worth preserving, even if we never again frame buildings entirely with green oak split by hand. It's knowledge about working with materials rather than just on them, about observation and adaptation rather than just specification and compliance. That approach to craft, that level of material intimacy, has applications far beyond medieval timber framing. It's what separates people who merely use wood from people who truly understand it. Medieval builders were the latter. That's why their buildings still stand, teaching us lessons we're only beginning to hear again.